I'm so pleased to introduce our speaker today, Dr. Alan Steinman, who is the director of the Helen Hunting Director of the Annis Water Resources Institute. He's been with Grand Valley since 2001, and he has an amazing list of credentials. He holds a postdoctoral research fellowship from Oak Ridge National Laboratory, a PhD in botany aquatic ecology, along with a master's and Bachelor of Science degrees in botany. A well-known expert in the aquatic ecosystems, his talk today will focus on the impact of microplastics in our Great Lakes. Just so you know, while he is giving his presentation, you will be on mute and your video will be off. But you do have a feature where you can ask questions of Alan and he will answer them at the end of his talk. Please welcome Alan as he talks about microplastics in the Great Lakes, separating fact from fiction. Welcome, Alan.
Thank you, Judy, and thank you to all the attendees out there in virtual land. What I'm going to do is I'm going to hide myself from the screen and focus on the slides as I move forward here. So bear with me while I do that. And here we go. I'm going to talk about 6 main topics today as part of this presentation. First, I'm going to give some general facts about plastics out there in the water environment. Then I'll talk about where they're found, human health impacts. Then I'm going to focus in on the Great Lakes and their impacts here in the Great Lakes, and then tell about a study that we've been doing out on Muskegon Lake in my lab. And then finally, when I've gotten you all depressed, I'm going to finish with some possible solutions out there to hopefully put a smile back on your faces. So what are microplastics? Well, very simply, they're plastics that are less than 5 millimeters in length. And how long is 5 millimeters? Well, here's a real life-size ruler. And you can see in this blue arrow here, that's 5 millimeters. It's about 1/4 inch. So anything smaller than that, as you can see on this fingertip, are considered microplastics. And we can classify microplastics into 3 main types. The first are primary, and these are intentionally made as being very small in size, the kinds of microbeads that are used in cosmetics, nurdles, which are basically the foundation microplastic for larger plastics, and abrasives. The second classification, as you might expect, are secondary microplastics. And these are not intentionally made to be small. Instead, they break down over time in the environment due to abrasion or wear, or due to ultraviolet radiation, or finally microbes may be working on them and breaking them down in what we call biodegradation. The third classification is not tertiary microplastics, as you might expect, but instead they're pyroplastics. And this is a new type of plastic that was found in the UK with some of our collaborators over there on the beaches. And we suspect that they're coming from the burning of other plastics as they are attempted to be gotten rid of from the environment. So what are microplastics made of? And we use the microplastic term very loosely. In fact, many of the elements that we find that we call microplastics are not actually made of plastics. Some are true plastics like polyethylene and polyester, but other materials like the particles that come off of our tires as we're driving on the roads, or the cellulose acetate that's found in cigarette filter butts, are not actually true plastics, but they're small, they're problematic, and we put them into this larger classification of microplastics. Well, in these slides, you can see kind of, and it's the kind of response you get. These are not obviously microplastics, these are macroplastics, but as they break down over time, they do form microplastics, and you get a sense of how ubiquitous and problematic plastics are in our waterways and on our beaches. It's estimated that over 8.3 billion metric tons of plastics have been produced to date since they first started being formed in the 1950s. And of that 8.3 billion metric tons, about 9% have been recycled, 12% have been burned, leaving 79% that have accumulated either in our landfills or in our oceans or in our Great Lakes or somewhere in that natural environment. So that's a lot of plastic that's out there doing its thing. Where do we find it? Well, virtually everywhere we look, we've found microplastics. It's in the atmosphere, it's in the dust. We find it in our food and beverages, which I'll talk about in a minute. It's in our cosmetics, in our domestic wastewater, our industrial wastewater, in the surface waters of our oceans and streams and rivers, and also in the sediments and soils of in our environment. Birds and wildlife, in the groundwater. Basically, everywhere we've looked, we have found some degree of microplastic contamination. It's really quite alarming and quite profound when you think about it. We get a lot of attention placed on straws, but also these disposable cups are a source of plastic, and they are very rarely recycled. Between 250 and 300 billion of these cups are used annually. And next time you have an opportunity to use one of these plastic cups, I hope that you will either use glass that will end up being cleaned or your own water bottle to avoid putting more of these into the environment. So these are the kinds of things that you can do as individuals to make a difference. Now, a lot of the plastic attention has received media focus because of the garbage patches that you hear about in the Pacific Ocean. We have the eastern garbage patch, the western garbage patch, and this convergence zone a little further north, where you can see very, very visually these large accumulations of plastics in our ocean. And it's, quite obviously, it's quite disturbing when you can see these kinds of massive amounts of plastics out there. In many cases, these aren't microplastics, these are macroplastics. Fishing gear takes up a lot of this that has just been disposed of or thrown over the side of boats, and it accumulates where these ocean circulation gyres converge. And you can see buoys in various states of disrepair and degradation, fishing lines, fishing nets, and other things like bobbers, and then other plastics also that you can see down here like buckets and polystyrene, bottles, bags, films, and toothbrushes will all accumulate in these garbage patches that we see out there. It also comes out of our wastewater discharge systems. Mason did a study a few years ago, and she and her colleagues they surveyed 17 wastewater treatment plants around the country, and they found that they discharge anywhere between 50,000 to 15 million particles per day out of our wastewater treatment systems. So again, the thought that these microplastics are being handled and filtered out by our wastewater treatment systems is just not the case, unfortunately, as much as we would like that to be. Most of the focus has been on the surface water, but in fact, a lot of these microplastics will settle down to the bottom of our oceans and our lakes and get into our sediments, and also be in our natural soils. A study that was done a few years ago found that in ocean sediments, like 16,000 feet deep, you can get up to 2,000 microplastic particles per meter squared in areas that you just would not expect them to be found. These tend to be denser materials that are going to settle out and not float like the polyesters and polyvinyl chlorides. And considering that most of the analysis that's been done to date by biologists and ecologists are focusing just on the surface water and not looking at the sediment, we know that the estimates that are currently made about microplastics are gross underestimates because there's a lot that's found down at the bottom. In fact, we sampled the sediment of Muskegon Lake last year, and here is a micrograph of that sediment on a filter. And you can see, if you look closely, these fibers. Here's a blue fiber here, here's a brown fiber here, and then these fragments that are all through here are all types of microplastics that are settling down on the bottom of our sediment. And I'll talk about Muskegon Lake a little later on. They're also found in our wildlife. Here you can see opening up a bird and it's filled with these plastics, just really, really nasty and unfortunate kinds of circumstances. And as you might imagine, these clog the intestinal ways of our wildlife, and there's no nutritional value that comes out of these. The most common material that's found inside the guts of these animals are polyethylene, polystyrene, polypropylene, and polyester. And the most common shapes we find are these fibers and fragments. They're also found in dry and wet deposition. A study done outside of Greater Paris found that microfibers in the fallout from the atmosphere, between 30 and 280 particles per meter squared per day. And then in Tehran, 88 to 605 microplastics per 30 grams of dry dust. So these microplastics are virtually everywhere. An analysis that was done based on the National Atmospheric Deposition Network found the highest number of particles per liter coming out of the rainwater was in this very remote area of Idaho in Reynolds Creek. And we could not figure out for the life of us why there were so many microplastics in this incredibly remote area until we thought maybe this is coming from forest fires. With all the fires that we had 2 years ago, the fibers will, the various microplastics will get up into the atmosphere associated with the burning and then get deposited when the rains fall further downwind. And we think that's what's happening here. Are there adverse health effects? These kinds of photographs on the left with the seal wrapped in these plastics are very evocative, very disturbing. But the reality is when we look at what the effects are on their health, on their reproduction, some studies have shown no effects, they're neutral, and others have shown some negative effects. So there's no universal kind of response that the literature is finding with respect to these studies. We're also concerned that in the making of these plastic materials, often heavy metals and additives are used. So it's not just the plastics clogging their intestinal ways, it's also ingesting these plastics that may have these toxic materials associated with the plastics themselves, or they can be absorbed to the outside of the microplastics, these kinds of emerging contaminants from the environment, what we call persistent organic pollutants, or POPs, can attach. And we'll talk about that in a moment. And when they do attach to these microplastics, they can become a vector for pathogens and viruses as well. So not just the chemical contaminants, but biological contaminants as well can attach to these plastics. And so these are the kinds of analyses that we're starting to do now at the Annis Water Resources Institute to see how big a problem these microplastics actually are. So what are the hazards? Well, obstruction of the digestive system if they intake these plastics. They can clog feeding appendages, as you can see in this poor sea turtle, clogged in a net. Obviously, when they get caught up in these kinds of problems, there's oxidative stresses associated with them, impaired reproduction, and then these bioaccumulation of these harmful chemicals that I was talking about earlier, the additives to the making the plastics, or these chemicals that may attach to the outside of the plastics that then get taken up by the organisms and may have toxic impacts inside the organisms after they're assimilated. What about human exposure to these microplastics? Well, studies have shown that humans consume over 100 microplastic particles per day, and we can inhale up to 170 particles per day from the atmosphere. Now, 100 microplastic particles, I mean, remember how small they are, less than 5 millimeters, probably not going to have much of an impact. But the reality is we are taking up these particles. We are not immune from them at all. Studies showing intake of bottled water, we can consume 23 times the amount of microplastics that are found in tap water. So our bottled water also is not immune from these microplastics. And what we found is these studies that are doing these kinds of analyses show tremendous variation in how much microplastics are being taken up. These are means that I'm showing you here in the first two bullets. And we attribute this variation to the fact that there's no standardized methods to analyze these microplastics. There's a lot of art to this and not so much science. And so one of the recommendations that people working in this field have said is that we need standardized methods for the analyses of these microplastics so that when we're comparing studies, we know that we're comparing apples to apples and not oranges to apples. Where are microplastics found in consumer products? Well, previously they were quite common in cosmetics, the microbeads and the abrasion that was used to clean skin, but now they're being phased out due to regulations. In bottled water, one study found that 242 out of 259 samples tested positive for microplastics with a range from 10 to 325. And again, just showing the variation that we have here because there's no standardized method for analyzing this. We found it in honey, up to 336 microplastics per kilogram of honey. Now, admittedly, these are very low concentrations, but we're finding them in areas that we wouldn't normally expect them to find. Salt, up to 280 microplastics per kilogram. Sugar, up to 217, and probably most alarming of all, at least for me personally, we're finding it in beer, up to 109 microplastics per liter, again, depending upon the kind of beer that you drink. It's even found in a very limited sample size of 8 stool samples. It's probably hard to get a lot of volunteers for that study, but nonetheless, better to be a volunteer than being a scientist analyzing it, I guess. We're still finding it in the stool samples, and the median number is 20 particles per 10 grams of stool. So it's really hard to get away from this stuff. And they persist a long, long time. Here you can see these are the number of years, not days, but years to degrade. Fishing line is estimated up to 600 years, whereas plastic bags are 20 years to degrade. So we're making a lot of it. A lot of it is not being recycled or reused. And what's left behind in the environment with these billions of tons of microplastics are sticking around a long time. All of that combines to make a very problematic situation in our environment. These are some of the additives that are contained within the microplastics, and plastics when they're formed. These are often very toxic and carcinogenic compounds, just to give you an idea. And they, as I mentioned earlier, they're sorbing biological materials. What we see, here you can see what they're microplastics or plastics that haven't been used are referred to as virgin microplastics. And here, after 3 months of incubation in Muskegon Lake, you can see these biofilms that form on the sides or outside these microplastics. And then they can carry different types of biological materials like viruses and pathogens. So this is a real concern that we have moving into the future. Are they toxic to humans? Well, the reality is that the effects on them are largely unknown. We need more studies that are done on human impacts. Again, the concentrations that we are taking up tend to be relatively low overall, but we need to know whether they're having an adverse effect, and we need to be studying them at environmentally relevant concentrations and in the presence of these additives, not on just virgin microplastics with the associated biota, the biofilms that form on them, and then these contaminants that we've been talking about, these toxic contaminants. So let's kind of migrate down into the Great Lakes and talk about where they're found in the Great Lakes, what they look like, how many are present, and are they as problematic in the Great Lakes as we have in some of the other water bodies that I've been talking about up to now. Well, the first rough estimate done this past year by Hoffman and Hittinger showed estimated that there were 10,000 metric tons, which is equivalent to 22 million pounds of plastic pollution that's introduced into the Great Lakes every year. 22 million pounds introduced into the Great Lakes every year. That's a number that should be fairly alarming. The USGS, the U.S. Geological Survey, a few years ago did a survey of 29 of the major Great Lake tributaries from 6 states and looked at the microplastics in these tributaries, and they found plastics in every sample that they took. Here's a map of the 29 tributaries that they sampled all the way up in Duluth, along the Door Peninsula, along the our area here in West Michigan, Saginaw Bay, and then down through Lake Erie and into Lake Ontario. And what they found is that the most common particle type in these tributaries was synthetic fibers, the kinds of fibers that would wash off of fleece and other textiles. And I showed earlier these wastewater treatment plants are not filtering out these kinds of fibers. They are getting into our waterways. Plastic fibers found in clothes and diapers represented 71% of the total particles. And microbeads, the kinds that are in personal care products, were the least common plastic found in the river water. And that's largely due to regulation when 3 years ago, the Federal Microbead Free Waters Act of 2015 was finally enacted. So that's good news that if we have the right motivation and the right political motivation and economic motivation, we can ban these microplastics and get them out of our wastewater streams. It's just that right now we haven't done it across all of the different particle types. Here's what some of these particles look like. These are taken again from that USGS study. You can see these fibers that are on these films, lines like fishing lines, pellets and beads, foam like styrofoam here, and different fragments. All of these are the different kinds of microplastics that we can find in our tributaries flowing directly into the Great Lakes. And here is the composition. On the right, the bar shows the breakdown of the microplastic types in the tributaries. Again, largely these fibers and lines that I just showed you. Once we get out into the Great Lakes themselves, it's largely fragments because these fibers and lines are relatively heavy and they'll settle out in the tributaries before they reach the Great Lakes, whereas the fragments are lighter. They're more likely to float, as are the pellets and beads, and so we see more of those in the open water of the Great Lakes. Survey was done again by Sherry Mason. She's been really one of the leading researchers on the microplastic and plastic pollution in the Great Lakes. And what Sherry and her colleagues did in the survey is they looked at the surface water throughout Lake Michigan. Here you can see all of the sampling sites that she found in Lake Michigan, ranging from the smallest triangle, which is 0 to 2,000 particles per square kilometer, up to the highest amount, the largest triangle, which is 50,000, which you can see right here. Now, I am not claiming that people are throwing garbage off the SS Badger, but I do want to point out this is directly in the line of their transit from Ludington down to Manitowoc. So whether that's related to the Badger or not, nobody knows for sure, but this is not an area you would normally expect to find the highest concentration of microplastics in Lake Michigan. Fragments were most common, followed by the fibers. The most common polymers that Sherry and her colleagues found were polyethylene and polypropylene. And the average abundance, when you look out through the entire Lake Michigan area, is 17,000 particles per square kilometer, which equates to about 1 billion plastic particles floating on the surface of the lake. And we know that this is an underestimate because she didn't look down in the water column or on the bottom of the lake itself. So, and as we saw earlier, there are quite a bit of particles, plastics down on the benthos or the bottom of these lakes. The majority of these particles are extremely small, not just less than 5 millimeters, but less than 1 millimeter in size. So for the organisms that are out there in the water column that are filtering, like our zebra and quagga mussels or like zooplankton, they're very easy for these to be ingested and to have potential negative impacts. Obviously, as you might anticipate, there are economic impacts from these microplastics. A study done in the UK looked at the global impact of marine plastics, and that the losses were up to $2.5 trillion each year from all of those plastics in there, either due to impacts to fisheries or tourism or other kinds of impacts. In the Great Lakes, as I showed just earlier, there's about 22 million pounds of plastic flowing into the Great Lakes each year. We know how important these Great Lakes are, and in particular Lake Michigan, as an important drinking water source, a source of food production like our fisheries, and obviously an attractive destination for tourism. So our coastal communities are particularly at risk to these potential impacts. If you have your beaches filled with these plastics, obviously people are not going to want to come and spend time at the water's edge under those conditions. So it's not just an ecological effect, it's also a potential economic impact as well. And then let me talk a little about the study that we're doing in Muskegon Lake over the last couple of years. And there are two parts to this study. We did a survey of microplastics in Muskegon Lake, and then we followed it up with an experiment to basically test what's going on with these microplastics. So with the survey, we surveyed two particular sites in the lake. We surveyed the open water of the lake by where our Muskegon Lake Observatory is, and we also sampled on the channel. And we used very formalized protocols that were approved by NOAA. One of the big problems when surveying microplastics is contamination, because so many people are wearing fleece or so many things are made out of plastics. You have to be very careful to make sure that the plastics in the environment where you're sampling are not contaminating your samples when you sample them or when you bring them back to the laboratory. And so we were very, very careful to avoid any of the contamination and had all the controls associated with this. What we found was the densities in Muskegon Lake in the open water by the buoy were about 31 particles per liter, and in the channel was about 12. And you're saying, well, what does that mean? You know, I have no context for that, so I'm going to provide you some context. It's very similar to what has been seen previously in Lake Superior, which ranged from 30 to 140, in Lake Huron from 50 to 400, and in the open water of Lake Michigan, about 91 particles per liter. So Muskegon Lake is not a major source of these microplastics. You wouldn't necessarily expect them to be, but it's still nonetheless, you know, good news and a good baseline to have for future analyses. What kinds did we find? Well, we found mostly fibers and fragments, and there were about twice as many in the lake as in the channel, as far as these types of microplastics. What color were they? Well, first of all, you're going to ask me, why do I care what color they are? Well, the color is very important because the organisms that are taking up the microplastics, many of them are visual predators, and they are going to basically consume different particles based on their color. So for example, if you have a zooplankton that likes to feed on phytoplankton, it's going to want green particles because that's the color of phytoplankton. And you can see that in the lake, we had largely green particles, but in the channel, we had none. Or other organisms, they want clear. They're focused on clear organisms that they're going to eat. And in the channel, we had a lot of clear, but in the lake, very few. So that's why it's important to be able to focus on the color as well as the type of the microplastic. So now we have good baseline information from which we can look at future changes in microplastics. For the experimental deployment, we looked at 3 of the major types of microplastics: polyester, polypropylene, and polyethylene. And we took known amounts of these microplastics and we incubated them at 2 sites and 2 depths. And then we went out and collected the water and the sediment samples at the time that we deployed them. And then we left them out after 1 and 3 months, and we collected them in these time periods. And then we looked for a whole suite of contaminants that had attached to these microplastics after these 2 time series. What did this look like, and where were they? We put the microplastics exactly where we had done the sampling to see what was in the lake. We did one in the channel, and we did another one out by our buoy. And this is what they looked like. We basically put the microplastics in these incubation tubes. Inside these tubes are wire meshes, which keep the microplastics in place. We didn't want to be a source of pollution as part of the study. And then we put these slip caps over the tubes, and then we attached them to the PVC frame with these tabs and quick links. And then we would take these and put them out into the lake to deploy them, as you can see here, at our 2 different sites and at our 2 different depths. And here is where, like the lake, just showing you a schematic. We had one at a 2-meter depth, and that was hanging vertically. Here are the different tubes in the PVC frame. And then we had another one at the bottom of the lake at about 40 feet that was laying horizontally. Unfortunately, this one in 2 meters, we lost. When we came back to retrieve it after 1 month, it was totally gone. I suspect that the torque from the forces associated with the cable somehow caused it to snap off, but we were able to retrieve the ones at the bottom at 1 and 3 months. And then on the channel, Here's the channel wall. Excuse me. Here's the channel wall. And we had one laying vertically along the wall, and then we had one down on the sediment laying horizontally that we were able to collect after 1 and 3 months. And then we went after all of these potential contaminants. These polyaromatic hydrocarbons are carcinogens. PCBs, as we all know, are problematic carcinogens. Organochlorinated pesticides are also potentially carcinogens. PBDEs are flame retardants and carcinogenic. You've all heard about PFAS from Wolverine up in northern Kent County and near the airports. We looked at some of the 7 of the major PFAS compounds, a series of heavy metals: chromium, manganese, copper, zinc, arsenic, selenium, silver, cadmium, and lead. And then again, we followed these stringent QA/QC protocols as part of this. This is done, these analyses were done with our collaborators down in Illinois who have been doing this for the last 10 years and have the instrumentation to do this kind of work. So the first question we asked, does the exposure, the 0, the 1 and 3 months, influence the absorption of pollutants and the biofilm on them? And here you can see very clearly, here's our virgin polyethylene after 1 month retrieval and after 3 months, that biofilms form and they get really slimy after 3 months. And this slime that's attached to them, basically bacteria, algae, fungal material, all of this makes a great absorbent for different types of these persistent organic pollutants. And so not only do you have these pollutants that's part of the makeup of the virgin microplastics, but you also have it attaching, absorbing to the outside, thanks to these biofilms. Is the plastic type an important factor in accumulation? And what role does location, the channel versus the lake, the surface water versus the bottom, play in the accumulation of these contaminants? So here's a data slide. I'm going to walk you through this. Don't freak out. First of all, I want to point out that this is the water column. All right, this has nothing to do with the plastics. When we put out the plastic, we also sampled the water column. And we have the channel at 2 meter depth at 6 feet, the channel at the bottom, the lake at 6 feet, and the lake at the bottom. Now remember, we lose the microplastics at 6 feet in the lake because basically the torque lost it, but we were sampling just the water here. And we can see that the blue bar, which is the PAHs, the polyaromatic hydrocarbons, toxigenic, carcinogenic, are the highest amounts that we find, regardless of whether we're at the lake or the channel, and we find more of them at the bottom than at the surface here. And these concentrations are about twice what you'd want for drinking water. So the pH levels are relatively high in Muskegon Lake, certainly higher than we'd like. The next highest tended to be PCBs, and these are relatively low concentrations of PCBs, much lower than they were historically, thanks to regulations that eradicated PCBs from our ballasts. So let's get into the plastics. And first I'm going to start off on polyester. And we're going to look at 3 different sites. Here's the water in the channel at 2 meters. And we're looking again, the same color coding. And by far, the 2 most problematic pollutants are PAHs in blue. Here's it right on the plastic. After 1 month, it goes way up, about 7-fold. And then it drops in half by 3 months. And then PCBs, which don't bioaccumulate, but we still have them on our plastics. What about at the next site? If we go down to the bottom of the channel, pretty similar kind of effect. We see that the pHs bump up and then go back down, and the PCBs are the next highest, but there's no sign of accumulation on the plastic. And then finally, in the lake at the bottom, again, pH is the highest, but instead of going down after 3 months, they continue to accumulate. And then again, PCBs. Let's look at the next microplastic. Again, I'm going to take you through the 3 same types of panels, but now we're going to go from polyester to polypropylene. And again, we see that the pHs go up at 1 month and then down a little bit after 3 months. And the total amount are pretty similar to what we saw in polyester. We go from the channel at 2 meters down to the channel at the bottom. Same trend. There's a little bit of bioaccumulation in PCBs, but most of it is in the PAHs. And then finally, we go into the lake. And we see the same thing where instead of going down at 3 months, the pHs continue to accumulate. And now finally, we'll go from polypropylene to polyethylene. And we can see again that the pHs bioaccumulate about 5-fold. They don't go down in the channel this time, they stay the same. But now the PCBs go up considerably, about 14-fold, and then come back down in the channel. In the channel bottom, we see what happened more similarly in the past, where the increase at 1 month, decrease at 3 months, and the same with the PCBs. And then finally, for the lake water bottom, it goes up for the pHs and PCBs, and then comes back down. So how do we summarize all of these data? Well, the pHs were by far the most prevalent persistent organic pollutant that we found on the microplastics. The channel sample concentrations peaked at 1 month and then declined at 3 months, where we saw the reverse trend in the lake. The highest concentrations were found on polyethylene, followed by polypropylene, and then polyester. So this says something about possibly regulating our microplastics in the future. The PCB accumulation we found was only on polyethylene. So there might be call for dealing with this particular type of plastic. And then for the other chemicals, which I did not show you because I didn't want you to get overwhelmed or overboard, but nonetheless, on the other ones, they were found in very small concentrations on the plastics after 1 and 3 month deployments. I want to spend a little more time on PFAS because it is such an interesting pollutant and it's got so much media attention right now. But first, I'm going to take a drink of water and move on. Before I get to the PFAS, I'll talk a little about the heavy metals, just this one slide. I'm only going to focus on polyester, but the trends were very similar on the other plastics. By far, the heavy metal of most concern was manganese in orange. We saw very similar trends to what we saw for the pollutants, where they went up and then went back down in the channel, and they kind of stayed the same in the lake. We also saw secondarily zinc as another pollutant in blue of concern here. So when it comes to heavy metals, the concern was largely with manganese and to a lesser degree zinc. It's possible that this may be part of the manufacturing of the plastic, because we did see it in the virgin plastics as well. The manganese and the zinc were most abundant and concentrated the most after deployment. And again, similar to what we saw for the PAHs, 4 out of the 6 channel water metals spiked at 1 month and then declined at 3 months. With respect to PFAS, now remember PFAS, the forever chemical, the one that has that very strong carbon fluoride bond, which is really hard to break down, and is causing all of the problems throughout the state and the country due to its presence in manufacturing and also in our firefighting foam. Out of the 7 PFASs that we did analyze for, these 3 were the most common. You may have heard of PFOA before, because that's quite a common one of concern. But our concentrations were really quite low. In parts per trillion, 2.8 and 3.3, nothing that would be overly alarming, and so that was the good news. However, the bad news is compared to what they were before they were introduced on the plastics, they're about 24 to 260 times the background concentration. The concentrations were really variable from one plastic to another, and this suggests to me at least that it's not so much the microplastics themselves, but it's how much and what type of biofilm is on the microplastic that is concentrating the PFAS on them as well. But even where it's being concentrated 260 times, the overall concentrations are not overly problematic, but certainly something that we're going to continue to keep an eye on in Muskegon Lake and other sites as we start doing more sampling. So in summary, within 1 month, some microplastics, like the polyethylene, would concentrate the POPs up to 380 times the background concentration we found in the water column. That amongst the heavy metals, manganese and zinc, were concentrated at the most from a minimum of 90 times to 600 times the background concentrations. There was tremendous variation in absorption of these, both temporally and spatially, and that we need to start studying the potential biological impacts in the water column associated with these heavy metals, and the persistent organic pollutants. Well, the good news is it's not too late. As I showed you earlier, due to regulation, we were able to get rid of the microbeads in our cosmetics. And when we look at pollution prevention, there is a hierarchy that EPA promotes. The best thing to do is source reduction, basically prevent it from getting into the environment to begin with. And then the next best is reusing, then recycling, treating, and finally disposing. The reality is we live in this throwaway culture, and it's really hard to get people to start doing these first two elements. But there's things that are out there. One of the ways to reduce the pollution is either through regulation, like bans, or using economic incentives, shown here in green around the world, or a combination of both, shown in purple. There's also private-public agreements. In areas where nothing has been done to date, like all of North America, we haven't tried to implement any of these kinds of things except on very, very localized bases, where, and even then there's tremendous resistance to trying to ban plastic bags or have any kind of economic incentive, unfortunately. But that would be one of the easiest ways and probably one of the most useful ways to do that. Reuse is starting to have some utility. There's a company called TerraCycle that's piloting a new approach that basically sends these reusable containers to consumers, like Pantene shampoo and aluminum bottles or Tide detergent and stainless steel. And these can be reused 100 or more times. Basically, the consumers use them and then send it back to TerraCycle to be refilled and sent back to the consumer. So there are opportunities. Wastewater treatment is sort of the last defense out there. They'd have to basically reformat what they do to get rid of most of the microplastics. For them, it must be cost effective and amenable to current operations, and that can be a real problem because right now they're already operating at the edge of fiscal solvency. So in summary, before we go to the questions, as hopefully you now have seen, microplastics are ubiquitous. Everywhere we look for them, we find them. In fact, we probably have them on the moon and Mars from the residue we left behind. They come in many types, many shapes, and many colors. The impacts to humans are unknown, but clearly an area of future focus. We need to examine both their direct impact, for, if they're taken up and clog the intestinal passages of systems, or more importantly, indirect, as we have been studying in Muskegon Lake, as they absorb these pollutants to them and have this secondary impact after they're taken up. And that viable solutions exist, but as in many of the cases with these environmental problems, there needs to be the appropriate economic and social policies in place and the desire in place in order to limit implementation. I just want to acknowledge some of the folks from my lab that have been heavily involved in this. John Scott down at the Illinois Sustainable Technology Center, who's done a lot of the analyses, and our various funding sources, the Alan and Helen Hunting Research and Innovation Fund that I hold at AWI, the Illinois Hazardous Waste Research Fund, our engagement with the folks in the UK in Birmingham, and then Illinois Indiana Sea Grant helped fund all of this. And with that, I am going to turn it over for questions. Thank you very much.
Have you tested drinking water that comes from Lake Michigan?
No, I have not personally. I know that the folks in Grand Rapids have looked at it, but as far as whether it's having any kind of toxic effects or not, that I'm not aware of.
Thank you for that. Another question, what type of filter, if any, would work, and would it take filter plastic fibers from the water exiting my clothes washing machine?
Well, one of the things that I have heard about is that there is a commercial product that you can put into your, I can't remember if it's the washing machine or the dryer. I think it may be the dryer. That will basically, you stick it into the dryer with that. It's kind of like a little bag or some kind of filter device, and it will absorb some of these fibers before they come out of your system. Or maybe it must be in the washing machine. That wouldn't make any sense to put it in the dryer. I guess you can put it in your washing machine and it will try and accumulate those before it goes out of the system and into the wastewater stream. So I would look that up, maybe Google that. Unfortunately, I don't know the name of it or the product, and I don't even know how effective it is. But there are, as you might imagine, when you start seeing these problems, a lot of commercial activity. I would make sure that you look at it carefully to make sure that this is some kind of snake oil sales product that's trying to get out there as part of greenwashing, and that it actually has some sort of third-party certification. But as far as filters from the wastewater treatment plant are concerned, they would have to be so small that it would take so much energy to push things through the rest of the wastewater stream through that I just don't think it would be technically feasible at this point.
Thank you, Alan. Another question, which is better for the environment, drinking bottled water or filtering your own tap water and drinking it?
That's a great question, and of course that depends on a lot of different components that you're looking at. I would argue that using tap water makes the most sense. It causes, whether you're talking about microplastics or talking about basically taking our groundwater, which in theory should be used for the ecosystem, and possibly having an impact on our systems. Now, there are a lot of groundwater systems in the state of Michigan that are basically having conflicts right now because they have been over withdrawn. That's a whole nother topic that we can talk about some other time. You know, Ottawa County is having significant groundwater conflicts. Also parts of the Thumb are having groundwater conflicts as well. So I think the more that we can use our tap water, most of the tap water, particularly in Grand Rapids, municipal water is coming out of Lake Michigan, and it's very, very clean, very pure. If your tap water is coming out of your wells, that's a whole nother story. You'd have to have them tested to make sure things like PFAS or other problems. But filtering tap water would be my suggestion for the best way to go, assuming that it's passed all of the health standards that need to be put in place.
Thank you, Alan. Here's another question. Is there any future for these boats, in quotes, I believe out of Japan, that go through the garbage areas to collect the debris and clean up the area?
Yeah, that's another great question. There are when you have these kinds of environmental problems, it also creates economic opportunities. And there are all sorts of different filter devices and boom devices that are being deployed right now to try and scoop up the surface accumulation of the garbage patches. You're talking about, hundreds of miles of this stuff. So it would take an enormous amount of effort to do this. And the hope is that you're accumulating it fast, you're removing it faster than it accumulates. But there are different devices. It isn't commercial barges that are going to remove the plastics. These are actually initiatives that are being done intentionally to go out there and do nothing but remove the plastics, and then basically take them back to land to be disposed of. But it is an enormous effort. You're 1,000 kilometers offshore just to get out there and then accumulate it and bring it back.
How much of the problem is from cigarette butts?
Well, on the beaches, it's a major problem. I mean, in terms of the numbers of, the types of types of plastics that accumulate. Overall, it's a relatively small amount. Same with straws. I mean, a lot of focus has been made on straws. And sure, if we can remove plastic straws, why not? But in terms of the total percentage of plastic pollution, straws and cigarette butts are a very, very small percentage. But if there's a bunch of them at the area on the beach where you want to be, you don't care about what the global distribution is. You care about the fact that they're next to you and they're disgusting and they shouldn't be there. Right. And so let's do whatever we can. These are relatively easy solutions in terms of not using plastic straws. And I wouldn't say stopping smoking is difficult. I don't know because I'm not a smoker, but my mom was, and I know how difficult it was for her to quit. And so whatever we can do to get people to stop smoking, if they do smoke, please take the cigarette butts out with you. Don't put them into the sand. That's just disgusting.
Yes, I agree. Any more questions out there? Well, I hope the next time we have you, Alan, we can all meet in person.
I would prefer that too.
This is really hard and challenging to not be able to be together, because that's one of the big important pieces of Grand Forum members. And while I'm talking, another question has come up. We all wear fleece. How can we eliminate the microparticles?
You can't. The fleece says it's, one of the functions of its manufacturing are these fibers that makes up the fleece. So I think that, the easiest solution, easy relatively speaking, is not to wear fleece. The second one is to look at some of these commercial products. And I apologize for not thinking ahead and trying to do a little research for you. But to see if something can be thrown into your washing machine when you wash the fleece to try and accumulate the microfibers before they get out into the wastewater stream. So take a look at that. I'll do the same, and if I can find anything, I'll share that with Judy, and she can share it with the Grand Forum members as well.
Okay, that would be great, because yeah, we all do love our fleece and it does keep us warm, but if that's a big issue, interesting to know that.
Well, I would hope that, companies like Patagonia, which are environmentally conscious, are also looking at these kinds of decisions and solutions as well. And maybe there might be something in the future that would be, if not eliminating the microfibers, at least reduce the amount that flake off during the washing process.
Right. Otherwise, we just don't do laundry.
There's another solution.
Right. That's one way to get out of it. Okay, well, Alan, again, thank you so much for being with us this afternoon, and we will see you in person the next time.
My pleasure, Judy. Thank you for the invitation. Best wishes to everybody. Stay safe.
Yes, and you too. And everybody stay healthy, stay home, and we will be together again next Monday when Paul Isley will be joining us to talk about economics. Thank you.
Bye.
Have a good rest of the afternoon.